Good day everyone, my name is Erick V. ALVIENTO and I will be discussing the topic Hall effect sensor under light electromagnetic. What is Hall effect sensor? A Hall effect sensor is a device used to measure the magnitude of a magnetic field, where VO is directly proportional to B and VO is equals to output voltage and B is the magnetic field strength. Hall effect sensors are mostly used for proximity sensing, positioning, speed detection, and current sensing application. Before going to the principle, what is the origin of the Hall effect sensor? The Hall effect was discovered by an American physicist Edwin Hall in 1879, with the basic physical principle underlying the Hall effect being Lorentz force. Lorentz force is the combination of electric and magnetic force on a point charge due to electromagnetic fields. As seen in the figure, Lorentz force is on a charged particle of charge q, which is in motion with instantaneous velocity v. The electric and magnetic force or the field vary in space and time. By interpretation of the graph, we will reach to the equation F is equal to QE, where it is the electric force, added to QV times B, which is the magnetic force. Here's a figure that explains the Hall effect. If we have a thin conductive plate as illustrated and a current set to flow it, the charge carriers would flow in a straight line from one to the other side of the plate. Once a magnetic field is positioned as shown near the plate, it will disturb the flow of a straight line of the charge carriers due to a force called Lorentz force. This means if we put a meter now between these two sides, we can obtain a measure of voltage. As we recall on the first slide, we said that the output voltage is directly proportional to the magnetic field strength. Indeed, it is correct. And this output voltage is also called the Hall voltage, and magnetic field strength is equal to the magnetic flux density. Thus, VH or Hall voltage is also directly proportional to the magnetic field strength or magnetic flux density. The analog output Hall effect sensor contains a voltage regulator, a Hall element, and an amplifier. As the name suggests, the output of such type of sensor is analog in nature and proportional to magnetic field strength, and the output of Hall element. These sensors have a continuous linear output. Due to this property, they are appropriate to be used as proximity sensors. This output Hall voltage is given as the equation VH is equals to RH times I over T times B, where VH is equals to Hall voltage in volts, RH is equals to Hall effect coefficient, I is the current flowing through the sensor in amperes, T is the thickness of the sensor in millimeters, and B is the magnetic flux density in Tesla. As observed in the graph, as the strength of the magnetic field increases, the output signal from the amplifier will also increase until it begins to saturate by the limits imposed on it by the power supply. Any additional increase in the magnetic field will have no effect on the output but drive it more into saturation. On the other hand, the digital output Hall effect sensors have only two outputs, the on and off. These sensors have an extra element Schmitt trigger added as compared to analog output Hall effect sensors. It is the Schmitt trigger that inducts a hysteresis effect, and so two different threshold levels are achieved. Accordingly, the output of the entire circuit will be either low or high. There are two types of Hall effect sensors, the bipolar and the unipolar Hall effect sensor. On bipolar sensor, these sensors require both positive and negative magnetic fields for their operation. Positive magnetic field of magnet's south pole is used to activate the sensor, and negative magnetic field of magnet's north pole is used to release the sensor. While on unipolar sensor, these sensors require only positive magnetic field of magnet's south pole to activate as well as release the sensor. On this slide, we will be showing how to use a Hall effect sensor using Arduino. Let us recall that the Hall effect sensor works on the principle of the Hall effect, which states that whenever a magnetic field is applied in a direction perpendicular to the flow of electric current in a conductor, a potential difference is induced. This voltage can be used to detect whether the sensor is in the proximity of a magnet or not. Hall effect sensors have three pins. the VCC, which is 5 volts, the ground, and the Vout signal. The pinout of a Hall effect sensor is as shown. The Hall effect sensor used is sensor US1881, and the other which is not shown is the non-latching sensor or the US5881. As shown in the connection, the VCC of the sensor is connected to Arduino's 5-volt power pin. The ground of the sensor is connected to the ground pin on the Arduino. The Vout or signal pin of the Hall effect sensor is connected to the Arduino's interrupt pin. Furthermore, a 10K resistor is connected between the VCC and Vout pins of the Hall effect sensor. This is done to pull the output of the Hall effect sensor to 5 volts. After connecting the Hall effect sensor to your Arduino, you need to upload the code to the board and test it. The Arduino Hall effect sensor code can be located in Arduino's website. It will be used to detect a magnet and count the number of times it detects it. Advantages and disadvantages. Advantages of Hall effect sensors is that they can be used for multiple sensor functions like position sensing, speed sensing, as well as for sensing the direction of movement too. As they are solid-state devices, there is absolutely no wear and tear due to absence of moving parts. They are almost maintenance-free, and they are robust, meaning strong and healthy. They are immune to vibration, dust, and water. Disadvantages is that they are not capable to measure current flow at a distance more than 10 centimeters. The only solution to overcome this issue is to use a very strong magnet that can generate a wide magnetic field. Accuracy of the measured value is always a concern as external magnetic fields may affect the values. High temperature affects the conductor resistance. This will in turn affect the charge carrier's mobility and sensitivity of Hall effect sensors. Here is the list of references used in the PowerPoint. Thank you.